this last lecture of this week. So I have taken you through a tour through this mix of algebraic geometry and coding theory. And what I still have to do is finish a little bit about decoding. Yeah, so what I said last time was that if we have some code given in space fq to the n, then this C has some parameters, namely the length, the k, and the minimum distance. And the decoding problem is the following, that given a vector in fq to the n, which we should interpret as somehow a distorted version of a code word, we want to recover that code word. So in other words, what we want to do, we want to find the closest code word. And here closest in the sense of the Hamming distance. Now I told you this is a difficult problem in general, but if we assume that such a code word exists with a Hamming distance from C to R less than or equal to T, with T, or rather 2T, less than the minimum distance, then this becomes a somewhat easier problem. So it means, in particular, that the matter of finding a closest code word here becomes finding the closest code word. Because if we assume that the number of errors that occurred, that the distance from the original code word to the received word is less than half the minimum distance, then this C is unique, and we can recover the original code word like that. So this was the decoding problem in general. And what we now need to do is to see if we can do this for these class of codes that I've constructed, for these AG codes. So in particular, I explained one possible approach to this, namely, so if we now pick for our C such a code, then what we can do is the following. So and we should choose an auxiliary divisor A, and the degree should satisfy that it is strictly less than n, the length of the code, minus t, where t satisfies this inequality. Okay, so we are trying to find then an interpolation polynomial q of y. So that's the goal, find q of y such that, well, there were a few properties. So the first was that this q of y had a very specific form. It was a degree 1 polynomial in the unknown indeterminate y, and these coefficients q1 and q0 lie in very specific L spaces, namely these two. And this is where this auxiliary divisor comes in. Now someone asked me, does it matter what kind of choice we make? Well, in this theoretical setup, only thing that's important is the degree. But if you want to make this fast, it may be wise to choose A and G more specific. So this was one thing, and then the second was that we wanted for all I, there is an interpolation property satisfied that this is equal to 0, where these Ri's come from the received word. So the input in a decoder is always this R that was mentioned here. So the coordinates of this vector come up there. So then we have seen that given certain conditions, we can find such a polynomial different from 0. Yeah, so if this t satisfied an inequality, or rather 2t, then we can find a non-zero solution. And moreover, we had that Q of f, where f was the polynomial, the function used to create the original code word, is a root of this polynomial. Yeah, so where the original code word, or the, yeah, let's say the code word we want to find, is c equal to this evaluation in all the rational places of this function. Now, I guess I didn't tell you explicitly what to do then. So what do we do now? So finding Q1 and Q0 is a matter of choosing bases for these two spaces, writing them up here in this expression, and then look at these linear equations. So then we have to solve a linear algebra problem. So finding the Q is simply a matter of linear algebra, Gaussian elimination. And by this choice, it is simply to guarantee that the number of equations is less than the number of indeterminates. So that is why there is a non-zero solution. So what do we do then once we have found Q0 and Q1? So because Q of f is 0, what we actually have is that Q1 times f plus Q0 is equal to 0. So finding f is easy. And there it is. Yeah, so finding the f, once we have found the correct Q, which really amounts to saying that we have found Q1 and Q0, we just do this simple exercise. And once we have f, we can construct a code word if we would want to. Yeah, so the last part is really simply realizing what this means. And this means that we can find f explicitly. Okay, so that was the first method that I talked about. And so if we look at this condition here, this is actually something we can recognize because this was the minimum distance, or at least the lower bound for the minimum distance of the code we started with. So this is a good thing, because what we want is that this 2t is less than d, but here we have to subtract the g's. So we haven't quite solved this problem yet. So one other remark is that, okay, here I've chosen such a CL code, an evaluation code as it is called. You could modify everything and also do the same for this C omega. It's a matter of rewriting some things. So that is not a problem. So we have still something left to do. We want to get rid of this minus g there. Now, as a startup for that, I started talking about a different bound for the minimum distance, but that is very much related with getting rid of this minus g. So what did I do? I specialized to a somewhat particular case where we say that the divisor g we look at is a multiple of a rational place. Yeah, it means that in this evaluation map we used n rational places. Well, we cannot use this one anymore, but otherwise we have still a lot of rational places to our disposition for making this evaluation map. So this is not a heavy restriction. And then what we said was, okay, we have associated to such a place a ring where we take the union of all L spaces of this type. And this really was a ring, and some of its properties are described by the so-called Rice-Strauss semigroup, which you get by taking minus the valuation of all elements of this ring. And this is not just a set, it turns out that it is a semigroup. So there was the Weierstrass-Depth theorem telling you that this is exactly the genus, and moreover, so it is a semigroup in the sense that 0 is in here, and if we have two elements, then the sum is also there. Okay, now to add a little bit to the notation we had, what I need, last time I chose functions f of rho from this ring such that the valuation minus the valuation of p of this f of rho is indeed rho. And I want to do this for all elements in the semigroup. Yeah, so what I'm essentially doing is saying, well, what I have is a ring here, and I can make a map to the Weierstrass semigroup by just taking minus the valuation. That is exactly the way I define this semigroup. It will have this as its image, and this is, so to say, kind of going the other way around. I just want to do that. But here there are many choices. So these f sub rho's are by no means unique, because you can always take one and add functions with lower pole order. Okay, then the next thing that I did was I defined a matrix M, which was made up out of code words of this form. I simply run through some elements of the semigroup, starting with the smallest, increasing until I have a matrix of full rank. So n is chosen such that the rank of this matrix M is small n. I got another question, namely, where did you actually use Riemann-Roch in your coding theory part? Well, I certainly used it when I was talking about the dimension of these codes, and that is CL and C omegas are, so to say, complementary constructions. But if you think about it, if you want to give a proof of this, you may also need it. So at least if you use it, you can very easily see that such an n will exist. Well, actually what you will need is Riemann's theorem. You don't necessarily need Riemann-Roch. Okay, so why did I introduce this matrix? It is simply because for any element from Fq to the n, I wanted to look at the matrix S of C, which was defined by M, and then a diagonal matrix with the coordinates of C on its diagonal times its transpose. And what we needed to know about this matrix was that, in particular, the rank of this matrix was the rank of the middle part, which was the Hamming weight of C, the number of non-zero coordinates. Okay. Now, since I will need it later again, I will write down one formula again that we also that I had on the blackboard last time. So I computed for a particular choice of C some of the entries of this matrix SC. So what we will need today is that if we choose C from this code, the dual code, and we moreover assume that it is not in a slightly smaller code, at least the general smaller code, where this degree, this integer m now becomes an m plus 1. So if C is not in this code, but it is in this code, then we can say something about it. Because it turns out that if we have a pair I, j such that rho I plus rho j is less than or equal to m plus 1, then we can write down, or at least say something about the ijth entry. Yeah, so the elements from my semi-group I just numerated, rho 1, rho 2, rho 3, and so on. Now if I have a pair I, j with this property, then we can say the following about this. This is going to be 0 if the sum of these two is strictly less than m plus 1, and it is going to be non-zero if these two add up exactly till m plus 1. Yeah, what happens if they add up to a larger integer? Don't know. Could be anything. So this is what we had. Okay, and this was enough to say that the Hamming weight of this C, of this particular C here, was larger than or equal to the cardinality of a certain set, namely the set Nm plus 1, which was defined to be all pairs from the semi-group adding up to m plus 1. Okay. Now, so I'm going to focus on this situation all the time. I'm looking at a code where it's satisfying these properties. Yeah, I know something about it, but now I want to investigate more closely what that exactly is. And moreover, I want to decode this code. I want to give a decoding scheme for this code now. Yeah, so you can see there's a slight discrepancy here, because here I was looking at the CL, here at the dual, so to say, the C omega. But this is not a real restriction, because anything you do for a CL here can be modified. Also, conversely, I will focus now on this code, but I could also reformulate everything for this. But I will just stick to this here. Now, the first thing that I would like to show is the property of these numbers here. Yeah, I would like to give a lower bound for those, so that we can see that the bound that we get here is not worse than the a priori bound that we had. Yeah, so what do we know anyway? So we already know that the minimum distance of this dual of dmp, so note this was just C omega dmp, is at least, well, what was it again? We have to take the degree of the divisor we used, which is m, and then we have to subtract g minus 1 twice, so minus 2g plus 2. So the minimum distance of this is at least this number here. Yeah, and now here we get another lower bound, or at least we get an expression for the Hamming weight, a lower bound for the Hamming weight of some of its cohorts. So let us see how these two compare. For any particular given semigroup, we can just compute this number. Yeah, for the Hermitian function field, I told you what the semigroup is. If we then also choose a particular value of q, we really get a series of numbers, and you can try to count these expressions. And then you will really see that these numbers you get will be at least as big as these. But to do that in general, there's a nice trick. So, it's the following result you get, a theorem or lemma maybe, I don't know. So if we pick an element from the semigroup, and we are interested in the cardinality of this, then this is going to be at least rho minus 2g plus 1. That is the result I will show. Yeah, so this rho can vary, but what we see here is that we're really interested in what happens if we have n plus 1 here. So if you, for the place of rho, write n plus 1, you would get exactly this expression. Yeah, so that result there will imply that all the numbers we get here, this number will be at least this. So let us see how to show this. It's a very compact statement, so it should also have a compact proof, so that doesn't always hold. So let us see. What can we do? So I'm going to introduce the following power series. We just define P of t to be the summation over all elements of the semigroup, and I just raise t to the power of that element. All the elements here are non-negative integers, so this is indeed a power series. Now the thing is, where do these numbers come from? Yeah, so recall what this n of rho is. So n of rho, that is all the pairs adding up to this rho. Yeah, so adding numbers here, and now all these guys appear in an exponent, really means that I am multiplying monomials. Yeah, so by the way, now I see I'm overusing rho a little bit, so let me change these guys to sigmas. Okay. So the trick is to look at the square of this power series. Yeah, so what happens if you multiply this with itself? So what do we have? We have t to the rho 1 plus t to the rho 2 and so on times itself. So if we start multiplying this out, then we will get sums of these kinds of expressions. I won't write down them all, but so we get these kind of sums. Now let me even write here rho 2 plus rho 2. So we get here sums of these kinds of elements from the semigroup. So if we take equal exponents together, what we get is exactly what we were looking for. So what we get is that, so as coefficient of a t to the sigma here, we get this number n of sigma. So they appear very naturally in this power series. So now it's just a matter of analyzing what's going on here. Analyzing these power series. So what can we say about P of t? So now we have to take a step back again. And can we say something sensible about this power series? Well, what we're going to use is Weierstrass gap theorem again. Yeah, so it is very close to the power series I would get when I take n as a semigroup, but because there are only g missing elements. So what we get is the power series you find using n, and then we have to subtract a polynomial which is the sum of g monomials. Yeah, so this q of t is just the sum of g distinct powers of t. That's what it is. Okay, so now we can compute p squared in a different way. This p of t squared is then apparently, well, this is nothing but geometric power series, 1 minus t, and then we have this minus q of t squared, which is going to be 1 divided by 1 minus t squared minus twice qt over 1 minus t, and then plus q of t squared. And that's all it is. Now let's see what happens here if we now develop this in a power series again. Well, this one is just a derivative of the one without the square. So here you get 1 plus 2t plus 3t squared and so on. And here, well, let me just leave it as it is, because what happens here, this q of t, I will leave it, is times the geometric power series, and then I have plus this q of t squared. Now let us read off the coefficient we wanted to know. So we want to say something about this number here, which is then the coefficient here of t to the power rho. So what is it? So from here we see that we get a rho plus 1. Okay, so now I can maybe not say really what it is because I don't know q of t, but what is the worst case? So here we have g monomials that are multiplied with all possible powers of t. So in the worst case, each monomial in here will be multiplied with something and give you a contribution there. So the worst case is that you get minus 2 of g. And what can happen here? Well, since this q of t is just the sum of monomials, all coefficients in here will be non-negative. So this is a correct bound. And this is exactly what I wanted. Yeah, so it's just a matter of setting this up with this power series and you get this result. Okay, so it means really that this bound we got here using some linear algebra is at least as good as the one you get using the algebraic geometry from before. But again, it's not surprising that you may get something better because we used a little bit more information. Instead of only the genus, we used a rise for semigroup. Okay, so with that in place, what I want to do is now start to look at the decoding problem again, because that is not completely solved yet. So I want to keep this because I will need that a couple of times later. So what is it we want to do now? So we, as a code, this one is no good. Maybe this one? Yes. As a code I take, as before, this one, and its minimum distance, this d that we have in this case, is at least m minus 2g plus 2. And now what I want to do is given r in fq to the n, I want to find the code word where it came from. Yeah, so what we are given is an r, which is somehow a code word we want to recover, plus some distortion vector, or error vector as it is called. And what we assume is that the number of coordinates that have been changed is not too big in the sense that this is equal to a t where 2t is less than this d here, or rather, let us say, less than this, because we may not know what d exactly is. So under this assumption, we want to find c. Yeah, so let me just write that. The goal, given r, find c. That is what we want to do. Well, equivalently, we may say find e. Yeah, if we know what e is, c is just r minus e. Okay, again equivalently, we may say we just want to compute s of e, where s is constructed in that way. Now, why is that also equivalent? Well, certainly if we have e, we can compute s of e, but the other way around is also possible because these matrices have full rank. Yeah, so you can always, given this matrix, recover the C or the E in that case that was used. Now, so what we want to do is somehow to find out what is this matrix S of E. Now, a priori it may seem that this is an impossible task because we don't know what E is. So how can we know what this matrix is? Yeah, however, we know a little bit anyway because this construction is really linear. So this S of R, that we know. And we also know that it is the sum of these two matrices. Construction is perfectly linear in the input here. Yeah, so this holds simply because R is C plus E. Okay, still, what have we gained? Well, we have gained something because we know some of the coefficients of S of C already. Namely, we know that it is 0 if this condition holds. So actually, we do know something about S of E. Yeah, so this is the whole thing. We will actually be able to determine this S of E completely. First using this partial information, and then there will be an algorithm to determine the rest of the matrix. And once we have done that, we are done. We have decoded it. Okay, so that is the goal now, to see how we can compute S of E. Good, so let me write here that we know that S of E ij is equal to S of R ij if rho I plus rho j is less than n plus 1. That we know. Yeah, so what this really looks like, if we try to make a picture of this, is if we have this complete matrix here, what we have is something like, that we have some partial information like this. Here we know exactly what S of E looks like. It is a shape that will in general look like this. And here we don't know it yet. Now the algorithm I'm going to explain is known by the method of majority voting. So I will use that language here as well. Although I don't know if voting is the right way to put it. But okay, let's see. So what is the input? The input is pure linear algebra approach. So just to have some terminology in place, let me give you a couple of definitions here. So if we have some matrix, it will be convenient to have some kind of notation for partial or submatrix or something like that. What do I mean? I just mean that it will be convenient to have a notation for the matrix you obtain from A by choosing out some rows and columns. So what I want with this notation is that here you pick out the first k rows and then you pick out the L columns, first L columns of that. Okay, now given that notation, what is it we can do with it? Well, now this terminology with voting and so on will come in. So let us see. The position I of j is called the candidate of A if, and then there's a condition, namely the rank of 3 matrices will have to be the same. So what are these 3 matrices? You get them by the above notation in this way. Okay, let me write it down first. Like that. Yeah, so there are 3 matrices involved here. So here we choose I minus 1 and j minus 1, and here we have increased the first coordinate but not the second. Here it's the other way around. Yeah, so what this means in a picture is that here we have the entire matrix we have position I and position j, and what we look at, so to say, this picture here. Here we have 4 possible matrices. The smallest one here, this one is slightly bigger. Here we adjoin this part, and then we have the whole thing. So what this property just says is that the 3 smaller ones should have equal rank. Now, so we're not looking at the whole ij part here. So these 3 should be the same, and if that is the case, the rank of these 3 is the same, it's called a candidate. Now, if we have additionally that the rank of, well, any of these 3, because now we know they're all equal, let me just write one down. If this is less than the rank of, and now we look at the full block, I of j, so if these ranks are not the same, then I, j is called a pivot, or pivotal position. Now these pivots, they have been well studied because they come up when you are doing Gaussian elimination. Yeah, so the number of pivots, for example, is exactly the rank of a matrix. So that is the meaning of these words. So just to put it, that the number of pivots of a matrix is equal to the rank of a matrix. Yeah, so we really can think of these as the ones that appear when you do Gaussian elimination. Only to keep the position fixed, we are not allowed to interchange rows and columns. But otherwise, we can just do elementary operations on the matrix, the other ones. So these tell you something about the rank, but it tells you more. It tells you, so to say, where the jumps in rank occur if you incrementally increase the number of rows or columns. Okay. So let's see. I think I can erase it now. Now the thing is that if we have these candidates, well, the thing is the name candidate is not chosen arbitrarily, so they can vote. So candidate can vote. What does it mean? It means that if we have a candidate here, so recall, it just means that the rank of these 3 matrices we were looking at is the same. Now, the terminology is that they can vote for a value of this. And what value will they vote for? A value such that the rank does not increase. Yeah, so it's a linear algebra exercise to see that if these 3 submatrices have the same rank, then there's exactly one value you can put here, such that the rank of the whole block will also be the same. Yeah, so that the rank will not increase. So, to put it in another way again, is that if we have a candidate there's exactly one value we could assign to this Aij such that I, j is not a pivot. Yeah, that is the whole idea with these pivots. It just means it has to be general, so to say. But yeah, if we don't want it general, we can actually assign a value, and moreover, it's unique. So this is the claim, and this is what we're going to use. This property is what we will use in the decoding algorithm. So what is it now we are going to do? So recall the goal was to compute C given R, which was equivalently compute this matrix S of E. And we were making a good start because it turns out that we already know quite a few of elements from this matrix S of E. Namely all the positions ij satisfying this inequality. So we already have some knowledge of this matrix in this area. Now the thing is, now to go further, what we are going to look at is exactly those coordinate positions where we have equality here. So what we are going to do is determine the next few. We're going to determine SE of ij where this rho I plus rho j is equal to m plus 1. Yeah, so it's not going to determine the whole matrix in one go, but we're going to look at a few positions where equality holds. Maybe it's there in this example. Yeah, so there are a few coordinate positions where we have equality, and we will now try to determine the values there. Now what is the idea? So the idea is to use this voting idea, to this mechanism with candidates and votes. Now, so what is going to happen for each of those positions where we have equality? Well, some of those may be candidates. Yeah, because in the definition of candidate, we don't need to know what this value is. It's irrelevant. It only depends on such a shape where this is taken out. So we can investigate whether or not those positions are candidates or not. Of course, we cannot determine if they're pivots, because then we would have to know their value. We don't know their value, but we have the notion of candidate for them. So this is the idea. So let me get some notation in place so we can do the verification later. So we have a claim here saying that let K be the number of pivotal positions of S of E. Yeah, in the known parts. So with coordinates, say I plus j, such that rho I plus rho j is less than m plus 1. Yeah, so we will in the end try to determine the number of possible pivots in this matrix SE. Well, this part we know already. So for each entry in here, we can check whether or not it is a pivot. Because then we only need to know this part of the matrix. So we denote that number of pivots in the known part of SE by capital K. Okay. So what do we know? So what is the rest of the claim then? There are at least, what do we say, number of n m plus 1 minus 2k candidates among all ij such that with, so we're now looking at all ij's where this rho I plus rho j adds up to m plus 1. And now I'm claiming among all those, so exactly among elements of this set essentially, there will be at least this many candidates. And the reason is that, well, there are a number of pivotal positions in the known part of the matrix. Maybe there's one here. Well, that one will knock out this one and that one. But any pivotal position will destroy the chance that one of these is going to be a candidate. Just checking the definitions carefully, this follows immediately. Because if we go from here to there, we already have an increase in the rank. Because this was a pivot. So this will not hold for those. But the good thing is, any one of those can knock out at most two. That's the worst case scenario. So we have this many candidates left. Okay, so now what we're going to do, so I don't remember why I wrote the 1 here, just erase it. So what am I going to do? Now I have a bunch of candidates and they are going to vote in this way, as I explained. They are going to vote for the values there. Now, the thing is, it would be nice if all the votes were actually going to give you the right values of these. But this will not be the case. So some will be correct, others will not be. So well, we have to investigate what is going to happen. So let me say T let T be the number of candidates from the above set voting correctly. Yeah, so what I mean here by the candidate is really this I of j satisfying this equality. I'm going to look at this set of candidates from the previous claim. Now some of them will vote for the true value, so which is where the t comes from, and then the other one is going to be f is the number that wrote the wrong way. Yeah, so what do I mean by voting correctly? It just means that this value that you would guess here, in this way, that you would assign to this unknown position, then you say, okay, this is going to be actually the SEIJ I was looking for, and the number of these candidates will assign a value that is distinct from this. So if you do it like that, then what is going to happen? So we simply have to investigate what is happening, what is most likely to happen. Okay, so what does it really mean? So what does it mean that you vote for the value that we thought it would be? Or what does it mean that here they vote for another value? Well, let us see what we can say about this. So, in the first place, we can see that, well, this number of candidates that we are looking at here is going to be equal to, t plus f, because we have distributed in these two sets. And we already mentioned that this number is at least this, minus 2k, that we already had in the claim. Okay. And then the next thing we would like to know is what can we say about the rank of this matrix? So I'm claiming the following, that the rank of this S of E is at least the sum of K and F. Now why is that? So I told you already that the total number of pivotal positions is equal to the rank. Now these K, they were once pivotal positions coming from this known part. So the rank is at least going to be those. But what does an F mean? What does that mean? That means that, well, if you would like in such a position to keep the rank here the same as it was in these smaller blocks, you would vote correctly for the pivotal position. What does it mean to vote in the wrong way? It is exactly saying that this is going to be a pivot in S of E. Yeah, so these are new additional pivots that we obtain in this procedure. So the rank will be at least the sum of those two. But this was equal to the Hamming weight of E, which we had said this was at most T. Yeah, so we get a basic inequality here. So now we have two inequalities to play with, and if we just manipulate these two a little bit, then what we get is the following. You simply get that T, starting here, is larger than or equal to F plus the cardinality of this set minus twice the Hamming weight. This follows immediately from those two, unless I made a mistake in my notes. Yeah, so here we have an equality comparing T and F. Now what we would like is that T is larger, strictly larger, would even be better than F. So what we want is that T is strictly larger than F, because that means that the majority of these candidates will vote for the correct value. Yeah, so then it is a matter of bookkeeping. We run through the candidates, they all vote for a particular value. If most of them will vote for the correct value, we can just look, well, what value occurs most often, that is the correct one, and then we can calculate from that the value for the others as well. So that's a detail I would like to hide for now, but I assure you, if we know one of these positions exactly, then we can compute all the others from that. Yeah, but now we know that the value that occurs most often, in some sense, gives you the correct answer. Well, I should still then investigate that this is not going to be negative, otherwise we have a problem. But it is not going to happen. Why? Well, we assumed that the weight was less than or equal to T. And what did we know about this? Well, this 2T was strictly less than this designed minimum distance, 2G plus 2, and that, we have just seen in the theorem up there, that I've already erased, is not going to be, this number is not going to be less than that. Yeah, so in fact, we do get a strict inequality, so we do get that T is strictly larger than F, and that is what we want. Yeah, so to really get the hang of this algorithm, there's only one way, and that is just to sit down and do it for an example. Yeah, so if you really want to understand this, I advise you to take a small example, take the Hermitian curve, Q is 4, and see how this works. So I'm not completely done yet. So you have to think about how to continue, because all I have done by now, if once you have run this, well, it just means that you know a little bit more of this matrix. Yeah, so you know a bit more. But now you can iterate. That is the beauty of it. Now you just iterate procedure. Yeah, so now you have exact knowledge of SAIJ. If rho I plus rho j is less than or equal to m plus 1. Yeah, so then you recalculate and you start looking at where the sum is equal to m plus 2 and you iterate the whole procedure. And then slowly you will fill out this entire matrix till you know it completely. And then you are done. Okay, that's what I want to tell you. Thanks for attending these lectures. And let me take the opportunity to thank the organizers for this entire week. So let me applause for them first.